Instructor slide and notebook. Artificial, no? No, not notebook. Instructor slide. Course introduction, I'm not touching. Introduction to deep learning also, I'm not touching. I'm directly going to artificial neural network. Okay, guys? Because uske pehle, whatever it is, just a self-read for you guys to do. Okay. What we will do is, instead of me speaking, I will take some rest, and such that everyone can understand, I will take volunteers so that the volunteers speak and then we will discuss it. Okay. If anything, like if there is something that you missed, I will help you understand. Okay. Okay. What happens is, in neural networks, as human brain functions or the nervous system of a human body functions, the fundamental unit is a neuron, and using neurons, the information is circulated in the entire body, right? How neurons communicate? One neuron is added to another neuron sequentially, parallelly, a lot of ways they are added, and these neurons combine together to circulate information throughout the body. So this is what we do, right? Similar to this biological neuron, there was something that was created called as perceptron, which acts as an artificial neuron, right? So the inspiration in order to create the artificial neural networks was a biological neuron. So if we are talking about artificial neuron, this is how it looks like. According, like similar to the biological neurons, we have these dendrites, right? Dendrites are the parts of the neuron where input is taken from, right? So this acts as the place where input signals are received, and this synapses, in synapses, these are axon terminals, are the places from where output is circulated, like output is sent. Now the good part is, output of one neuron acts as input of another. It means other neurons, synapses, will get connected to the other neurons, dendrites, will get connected to the synapses of this neuron, right? So this is how these neurons form a chain, and these are efficient enough to circulate information throughout the body. So similar to a biological neuron, we have something called an artificial neuron, right? Here you are able to see this artificial neuron, guys. Here also we have multiple input nodes. Now along with every node, we have some weights assigned, okay? Now what is the purpose of weights? Anyone would like to tell me? Why do we assign weights to these neurons? Sorry, to these input nodes. Anyone would like to comment? Anyone? Any other responses? Not about speed. These weights actually help decide the decision boundary, right? So input can be anything. Let's say the input is 0.1 and 0.2. But if I want that the output decision boundary is 0 and 1. So in order to make sure that these inputs are inflated such that I have a clear decision boundary, I use weights. That's one of the most important reason, right? So that the inputs are amplified and then we get a clear separation at the output. Then accordingly, if we provide weights, we will get a control over the activation function, right, guys? We'll have a better control over the activation function. Apart from that, we can do bias adjustment as well. So depending upon the weight we can consider as biases, right? How much bias we want to add. For example, if there is zero weight, what does zero weights mean? Zero weight means that whatever the input is, I don't want to give any value to it. This is what we did for L1 regularization. Guys, you remember L1 regularization, in which we reduced the coefficient of few input variables to 0. So here also, if the weight is 0, it means that input has nothing to do with it. So how they are added is, we know the equation of straight line, y equals to mx plus c. So x is similar input value. The slope in straight line equation m corresponds or equates to this weight w. Okay, so this is nothing but the slope, like if we compare it to an equation of a straight line. Okay, guys. Now what happens is, these input values gets multiplied with the weights, and we sum this up. For example, x1 w1, x1 into w1 plus x2 into w2 plus xn into wn. We combine the sum, and then what happens? We pass it through an activation function. Wait. Where is the activation function? Yes. And then we pass it through an activation function. Now, what is the purpose of activation function? The purpose of activation function is trigger this output only if this summation functions returns a particular value. If it is not able to return a particular value, above a particular value, do not return anything. Okay. So that's what activation function is. Please repeat the last statement. Prashant, you were also not present, or you were present? Tell me first this. Arunis, you can go through this when you have time. I sent the below. Hello to faculty, I just wanted you to know, did not want to disturb others. Guys, give me 1 minute. Now we have moved on to perceptron. Okay, so what we are going to do is every day we are going to like give at least 15-20 minutes to the previous sessions, like from recommendation engine and unsupervised learning algorithm. Why? Because from the content point of view, like 40 hours or let's say 48 hours is not at all enough time to cover this much content, like to cover it properly, right? So obviously there are some topics that were not covered properly. So I'm giving this 15-20 minutes time every session so that we can cover those topics, right? So yeah, this is how we have planned. And in order to compensate for the same, I will also extend the session by 15 minutes. So that won't be a problem. Okay. I hope it helps. Okay, guys. Then feed forward neural networks we will study today in details. Multi-layer. Okay. Let me tell you one thing. For those who were absent yesterday, right? A perceptron is nothing but a human neuron, right? How it works is this is the basic structure of a perceptron where there are multiple units, weights added to it. There is a summation function which does this job, this x1 into w1 plus x2 into w2 and so on, right? After doing so, it passes through an activation function where it will only turn the output as 1 if this summation value is greater than the preset activation function, that is threshold. So let's say threshold is 0.5. So if this summation function is giving output as 0.5 or more, then only the y predicted will go to 1, else it will continue to be 0, right? And in this particular part, we don't see a hidden layer, but in actual, what happens is the perceptrons or the feed forward neural network, they have one hidden layer. What is the purpose of hidden layer is it actually makes the processing very easy. Like we have a complex data set, right? The data set are complex, the machine learning algorithms are complex. So the that's why we are using deep learning. Now now what happens is if we don't have a hidden layer present, like if we don't have an additional layer present, it will not be able to process all the complexities that are present. But the user, at the other hand, does not need to see the hidden layer, the middle layer, right? So that's why we call it hidden layer. The user only needs to see what's coming as part of input and what's coming out as part of output, right? So that's why any particular layer apart from these input and output layer are called as hidden layers, right? Now, in a normal perceptron, we have only one hidden layer, and in case of a multi-layer perceptron, the number of hidden layers increases. That's it. It is greater than one. Okay. This is like this is single layer perceptron, obviously. So here, if the hidden layer increases from one, this is one layer, right? If it increases to two or more than two, it becomes a multi-layer perceptron. Everything is same. One second. Hmm. Now we will talk about activation function, guys. We did not cover activation function last class, right? We will continue today. Please correct me if I'm wrong. I guess we will continue activation function today. Perfect then. Let me draw something for you and explain. Okay, that way you will understand it better. Excali draw. One second. Okay, guys. So just imagine that we have an input, okay, where the input line, sorry, we have an output, and the output line goes like this. And this is my threshold. This is my threshold, which is 1. Okay. This output line that you are able to see is the output from perceptron. But if we apply activation top function on top of it, tell me, if the threshold, preset threshold is 1, if the preset threshold is 1, what happened? Okay. Then what will be the output after it crosses the activation function? What will be the output from here? It will be what, like it will be let's say this value is, on an average, this value is 0.34. So what output I will get here? Will I get 1? Will I get 0.34? Or will I get 0? What do you think the output I will get, guys? Please comment. 0. Why? Because it has not went past the threshold. Now consider something different. Let's consider something else, like this. Like this. So here, what will be the output? Now tell me what will be the output. No, the output line will look like this. I will draw it for you. The output line I will draw with blue. It will continue to be 0 till this point, 0 till this point, and as soon as it crossed the threshold, as soon as it crossed the threshold, it will start to give 1 as the output, right? So here the output will be 0 for this part, and the output will be 1 after that. Understood till now? This is the purpose of threshold and activation function. Now, till now the basic is clear, I hope, right, guys? Everyone, just give a quick yes that the basic is clear. Guys, till now it's clear, right? Please confirm. Hmm. Based on data, we will get 2 outputs in activation function. Exactly. Like I will tell you, like there is a lot more to it. Okay, Prashant? Yes. So consider it like mic. Okay. Consider not a mic, a filter, low pass filter. Okay. So what happens in low pass filter? That it continues to remove all the noises till the noises reach a particular limit. Let's say you have a music system in your car and you have set the low pass filter to 50 hertz. So till the noise or till the sound reaches 50 hertz frequency, you will not be able to see anything. But once the sound crosses 50 hertz, you will be able to see it as an output in your speaker. That's called low pass filter. Got it? So it's not 2 output you are getting. It's something that once the output value crosses the threshold of the activation function will trigger the output as 1. Till then, it will continue to be 0. So it's not 2 output that we are getting. It's by default 0. And once it reaches the threshold and crosses the threshold, we get 1 as the output. Understood? Okay. Now let us proceed to take some other examples. By other examples, what I mean is, I explained why it is crucial. These are the mainly used activation functions in market. Okay. The step function, the sigmoid, the rectified linear unit, and softmax. Only output, only output. That's a great question, Sina. Only output layer. Once it goes to the output layer, then only it will have the activation function. This is how it is set up. Okay. So these questions they also ask you in interviews. Hmm. This is a step function because there only we need to control the output, right? Why we need to control it in the hidden layers? There is no point to control in the hidden layers. Once we get to the final output, we can control it. Why control it multiple times? Got it? There is no need actually. Okay. Who would like to explain me this step function? What do you think? It is the same thing that I just explained, right? That till it is, what do you think here? What happens? 1 second, guys. Sure, sure, Saha. Let me try to unmute you. Where is Saha? Hey, why am not able to find Saha? Yeah, Saha. Unmuted you. Saha, unmuted you. No, 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 we cannot hear you. Okay. So, what happened? 1 second, guys.
Can you
Want to-
hear me now?
Yeah, yeah, we can hear you now.
Sorry, there was a mic issue. No, I think this is like the step function is kind of a, as the name says, it's activation function. It is similar. They have brought it similar to that of the neuron. Actually, what the neuron scientists found out is uh, the input functions, when they add up, it should come up to some threshold that should actually activate the neuron to create the impulse, right?
Yes.
So it must be like a trigger. So this activation function, when we do all the linear activity, the output should be matching this threshold. Once it reaches the threshold, either it's 1 or 0, right? So if the summation is activating this function, it will just become 1 and it will say positive. Okay, it will respond.
A
So
matter of time, right? Like
uh,
it's like a toggle switch. If threshold is crossing, then toggle 1. If it comes down below threshold, toggle 0. Simple. Okay.
correct,
So
correct,
it's
yeah.
like the electric switch at your home. On,
Like
off, on, off.
transistors. In transistor, when level comes, it becomes a switch, right? That
Yes,
base
yes, yes.
current goes, yeah, same, yeah.
Mm, exactly. Okay. So that's a step function. Now talking about the threshold, I can say here threshold is 0. That's what. I'm coming to threshold. Hold on. Now talking about threshold. By default, the threshold is 0. And if you want, like if it is a negative value, the step function will give what output? 0 output. And as soon as it gives a 0 or a non-zero or a positive value, as soon as it is even slightly above 0, it will start to give output as 1. So the threshold is by default set at 0. Yes, there is an option to set the threshold to any value. So it's like you can set the threshold at 2 also. That only if the output is greater than 2, my step function will be activated. Now, the question is, once step function is activated and threshold is 2, what is the output will you get? Will you get 2 as an output or 1 as an output? In mm, okay. So right now in this example, what I showed, the threshold is 0. So if like greater than 0, whatever greater than 0, if it is a negative value or a 0 value till that point, the activation function will not trigger the output, output neuron, right? But once the output goes above 0, anything above 0, the step function will trigger the output function and it will continue to give output. Now, according to step function, the output is 1. So it will give 1 as the output. Fair enough. But suppose the threshold is 2, right? And consider a time that output crosses 2. So then only activation function is activated and we will get the final output. So the final output will be 1 or 2. 1. Why 1? Because in artificial neural network, we have only two defined outputs, either a 0 or a 1. So it cannot be greater than 1. That's what activation functions do. They channelize or they limit our output levels, right? So we need to make sure what output do we want. Got it? This is one more purpose of step function, like activation function actually. Now, let's proceed to another one, sigmoid function. It is almost similar to a step function, but there is something different. What is that? Here, this also produces an output in the range 0 to 1, making it useful for binary classification tasks. In step function, where is it? It adds non-linearity. Since sigmoid function like basically works on probability thing, yes, I have to agree to it that it adds non-linearity. Why? Because it acts on probability. So that sigmoid curve is there. Anyways, so what is the basic difference between the step function and the sigmoid function? It's written only. The sigmoid activation function produces an output in the range of 0 to 1. So it's not just 0 or 1. The output is 0 to 1. So it's a continuous thing that you are saying. It's not that, yes. So it's not that the output is just like at in a single point only it goes from 0 to 1. No, it's not like that. In sigmoid function, what happens? It's a continuous curve where the values increase gradually, right? Understood, guys? Now, this is my favorite one. What is this? What is this, guys? But I will tell you. I will tell you. I will tell the use of each of this. Let's first understand each of this. Then I will tell you the use each of this. Okay. Instead of me telling you where to use what, if I give you the context, it will be better. It will be better for you, right? So this is rectified linear unit, ReLU. What happens here? Would someone like to come out of mute and explain me? Guys, would someone like to come out of mute and explain this? Mm, not only removes negative. Let's get more examples, more responses. Either zero or other values. What are the other values? Be specific. Try to be specific. We can see it here. So the output is equals to the input value itself. Someone was asking, no, what will be the output? How can we determine? So consider a case where you require, like after it reaches a particular threshold, the output should be equal to the input value. Like the output should be equal to X. So there just use rectified linear unit, ReLU function. Hmm? Output is not limited to one. Exactly, guys. Exactly. So this is ReLU. So till a particular point, the threshold is crossed. What happens? The output is zero. Else, the output is equals to the input value. Similar, simple thing. And then comes the like one of the most widely used, the sigmoid, sorry, the softmax function. But it contradict. I guess Vijay has tried to write contradict, but it contradict fundamental where output can be zero or one. Again, I'm saying no. It depends on what you want to do. What is your requirement accordingly, right? So it totally depends upon the requirement. What we'll have to do if we are using ReLU, like obviously the requirement is not that I will just need zero or one. I might need something else as well. It's not that these functions are used only with ANN and CNN and RNN, right? They are used at multiple places, right, Vijay? Got it? Yeah. But yeah, this can also be used with NNN. Some modification needs to be done, but yeah, we can use it. Now coming to softmax function. Now, would someone like to try this? What happens is softmax function deals with probability distribution. That's number one thing. Number two thing is this function is used for multi-class classification. What it does is it transforms a vector of raw scores into probability distribution. Okay, so raw scores are there. It transfers to probability distribution where each element is between 0 and 1 and sum of all elements equals to 1. So if you sum up all the inputs and do this cumulative, like go through this cumulative curve, the softmax curve would reach 1 when you reach the summation of all the inputs. And individual input, they can range from 0 to 1. So that's the limit. Okay. Now, why and how it is used? It is used for multi-class classification. Okay. Um, the key characteristics are probability distribution, differentiability, exponential effect. So here, exponential effect is there. So once it starts to rise, um, it goes through very rapidly. Now, let's talk about the use case. Definitely. I will repeat, but let's talk about the use case, then you will understand it better way. Okay, Sheena? Only softmax only, huh? Let me start from the use case of softmax and then I will go back. So I told you one thing that softmax is used for multi-class classification. So it is typically used in the final layer of a neural network where there are multiple classes. Number one. Number two, the network outputs a vector of logits. And once we apply softmax function, these logits are converted into probabilities for each class. Simple. So suppose there are three classes, those three classes will give some value, right? Logits. Once softmax function is applied on those values, it gives probability distribution for each of these classes. And we know, right, whichever is having the highest probability wins, or that particular class depends, like is assigned to that particular value, right? So that's softmax function. Now, in case of softmax function, what happens is it consists, or better I would say, it considers the entire vector of outputs, not just one output. Softmax functions deals with the entire vectors of output, where it calculates, sums up the values of output for the entire vectors which are part of the network, right? All the input vectors that are present, it tries to calculate the outputs of the entire vector. Can you write? And so I'm not able to. Okay. Then let's take a small break, and then we can like go to Scaly draw. I will write it and show it to you. Okay. Mm, better let us do this, or else like we will reduce the continuity. Okay. Mhm. Let me show it right away. Else continuity will be broken. I don't like that. I will give you an example. Suppose where x is equals to, let's say 2 comma 1 comma 0. Okay. Now what will happen is we will basically exponentiate each of these logics. So step 2 would be, so exponentiate each logic means e to the power 2. What is e to the power 2? It is equals to e to the power 2, 3 point something. So 7.2 something. I'm not sure if I'm correct. Someone can calculate and let me know. And e to the power 1, it is equals to 2.7. That's easy. And e to the power 0 is what? Is equals to 1. So in the second step, we exponentiate this each logit. And what we do is these vectors, the exponentiated vector is this e to the power 2, e to the power 1, e to the power 0, which equates to 7.2, 2.7, and 1. Right? Now what we do is we basically compute the exponentials. Right? So the sum would be 7.2, 2.7, 9, 10, 11. Let's say somewhere around 11, the sum. What we do is then normalize to get probability. How do we normalize to get probability? So probability for first, that is e to the power 2 was there, right? So the first one is, let's say 7.2 divided by 11. So it would add to 0. I believe 6. Let's say 6. Probability of the second vector would be how much? Is equals to 2.2 divided by 11. It would equate to somewhere around 0.239, something like that. Let's say 24. 6624. How much it goes? 89. And probability of 1. Here it is equals to 1 by 11. So 1 by 11 equates to how much? 0.090. So all of these values, if we add, these values will get to 1. This is what I was saying when I was trying to explain this. When I add up all the values, the softmax score would go to 1, and individual values would be having scores of, like, the probability scores between 0 to 1, right? So here it is 0.66, 0.24, 0.9. So this is how softmax function is calculated. It is not calculated for one output, but for the entire vectors in the, like, for the entire vector. For example, here, let's say it was having 3 rows. In our database, it might have 1,000, 2,000, 1 million rows, right? So it will calculate the logits. Logits means these values. It will exponentiate it, and then it will calculate, it will sum it, and then it will calculate the probability distribution. And once that is done, we will get the softmax score, which looks something like this. Control Z. So consider the number of input variables are 1,000, right? So it starts from 0 here, it goes at, let's say, 100 here, and at the end it is 1,000, right? And the total score should not cross 1. So it starts from 0 and it goes till 1. So each unit Each logit will have its own probability. Here we are getting normalizing it to get the own probability. So when we add this cumulatively, it will form a curve like this. Oh, sorry, Control Z. It will form a curve like this, where it will eventually go and reach the value 1 when it grabs all the 1000 value. So it is definite that the total sum of probabilities of all the values would be 1, where we will also get an essence of the individual unit probability, and that is softmax function. Now, how it is important? It is important when we try to calculate multi-class probabilities. So here you can see we are able to calculate multi-class probability. So that's where softmax function is useful. Is it clear, guys? Guys, is it clear now? Please comment, everyone. Any questions? Hmm. It can be more than 3 classes as well. No, it acts on all the classes. So it tries to find out how many classes are there in the like data, and then it acts accordingly. How it will get interpreted here. See, I interpreted na the first class, second class, and third class. These are my probabilities. This is the output value that we have. So in order to get the y value, the target value, we do a lot of processes, right? So here I did not do any processes. Instead, from the input value x, I directly got the output value y by one operation by applying some process on top of it. So y equals to e to the power x. Here I did. Okay. This is how I implemented. So this is y. This is nothing but y, where I proceeded to first find the sum and then normalize it and then proceed further. Okay, Sina? And how to implement it in general, like how we are going to implement it when we do the notebooks, that too we are going to see anyways. Here you see the probability for uh, 2 goes in the first, second. Okay, here I miswrote it. Thanks for letting me know. Huh? So here it will be the third class basically. Third class. So first I wanted to say this, second I wanted to say this, and third I wanted to say this. Okay, now clear? Here maybe you are trying to complicate it too much. What I want to make you understand is softmax, yes, are the 2 inputs, and we perform some operation on top of it. These are my 2 outputs. So probability for first input, first, like we are talking about, it needs to map to 3 classes. Yeah, the 3 classes are there now. 3 classes are there, 2, 1, and 0. Let's say these are the 3 classes on which I am doing some operations. Very simple to understand, right? Don't overcomplicate it. What's so complex about it? I'm not sure. Here the main idea is to show that whatever be the number of classes, it basically considers all of them. But in the other activation functions, it considers about that particular output only. But in softmax functions, number one, it considers all the outputs together. It gets a probability distribution, and then this is how it actually helps in multi-class classification, where it is able to take the probability distribution of all the available classes, and whichever class is having the highest value wins. No, no, no. If you did not understand, let me know. Where is the problem? I will help you understand. Why proceed? Let's get it cleared, and then only we can proceed. Tell me, no, Sheena, would you like to come out of mute? Sheena? Yes. Yes. Then let's say these three, it needs to map to 3 classes A, B, C. So let's consider these 3 input are finally going to go to 3 different classes. We can consider so, no? Let's say the process is such, or the function is such, that 2 will map to A, 1 will map to B, as you mentioned, and 0 will map to C, as you mentioned, right? So based on the function, the value we are getting for the output values or the output classes, what is going to be the probability? 1 second, guys. 1 second. It needs to map to 3 classes ABC. So is that clear now, or still confused? I am extremely sorry. Maybe I'll go to my end. I did not get it. Okay. Let's continue. I will like take this at the end of the class. Okay. Let's continue. Okay, Sheena. Yeah. Let's take a short break then. I will run the poll. Let's take a short break after that and we come back and we proceed. Please vote the poll, guys. Okay, guys, I have shared the results for the poll. Let's take a break, a 15 minutes break. We'll be back and we'll resume. Okay. I'll go on. Guys, am I audible? Can you please confirm in the chat box? See your chats. Guys, am I audible? Okay, awesome. So let's proceed. Hello, 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 hello. Guys, is the sound better now? I'm just using headphones. I hope it would be better right now. I guess so. Okay. Now, let's talk about where to use which activation function. So let me open the chat box real quick. Guys, what do you think would be the applications? Now, before I go ahead and explain, do you have any idea about where to use which step function? Guys? Okay, step function, Saha is saying in case of simple classifier, step for like boarding bus or not, eating or not, going office or not. Very good, Vijay, very good. Sigmoid, so I will try to sum it up for you guys. Okay. Step function can be used anywhere where we have binary decision making, right? Like whether a neuron should fire or not. Sigmoid function, here also the use case is binary classification or logistic regression. So we can use the sigmoid function not just for classification but for logistic regression as well. So that's the yeah, exactly, probability distribution. And since we have already studied logistic regression, we can use the sigmoid function, activation function, in terms of logistic regression as well. Okay, along with binary classification. So what are the characteristics if we are trying uh, sigmoid function? What is the characteristics? The characteristics is there will be a smooth transition. So it basically offers a smooth gradient, which makes it possible to perform gradient descent, right? Uh, so if we are using step function, it would be hard for us to reach at a particular convergence point. But if we are using sigmoid function, it would be very easy for us to perform gradient descent and reach that convergence point. Now, what is gradient descent and everything? We will just like study. Okay, don't worry about it. Gradient descent is basically used to reach the convergence point or reach the point where cost function is minimum. Okay, how it is done, we will see. Now, a ReLU unit or a rectified linear unit. So here the use case is basically image recognition. It can be natural language processing and other complex tasks. Okay. And one thing I wanted to tell you is someone was asking, right, these activation functions we can use like only in output layer or where. So ReLU functions actually can be used in hidden layers in deep neural network, because here after a particular threshold, they mimic the input variable, right? So once a threshold is reached, they mimic the input variable. So the neurons can be fired. The hidden layer neurons will be fired only when it reaches a certain threshold, and then will mimic the input only. So the output will be equals to what the input of previous neuron was, right? You understood, I hope. But it will happen only after it reaches a certain threshold. So that's the benefit we do in ReLU. We use in ReLU. And softmax function we have already discussed, right? That we use it for multi-class classification. We use it for probabilistic interpretation, right? So let me give you a visual representation of the same. It will be easy for you to understand. Okay. So what I will do is I will try to give you a visual representation by drawing something for you. So let's say this is my input data. You can also take a screenshot of the same after we are done drawing this. Okay, guys. So consider this is input data, and then we have this hidden layer. right? In this hidden layer, then we come to the output layer. Let's talk about the scenarios. If it is having some binary task, we can use sigmoid where the decision is based on probability between 0 to 1, right? So even though it is a binary task, the decision is based on probability, and where we can modify the threshold as well. Then in case of multi-class classification, what we use? We use softmax. Here, the technique used internally is probability distribution. And make sure this probability distribution is across the entire input vectors, okay, not just one. Now, if it is a simple logic, like yes or no, something like that, we can use 0 or 1, right? So there we use step function where the decision is not based on any probability. Okay, guys, you can take a screenshot of this, everyone, and let me know once done. Okay, we'll proceed further. Everyone, please let me know once you have done taking the screenshot. Okay, everyone. Perfect. Everyone can download if some has not taken it. Okay, we'll proceed then. So activation functions we have done discussing. Now there is an assisted practice. Let's understand the concept of neural networks and activation functions using Jupyter Notebook. So here we are not going to implement something, but just understand how to use it. Okay, guys? We are going to study how to use it. That's it. So let's proceed. File, upload, browse. Okay, guys. So what are the steps that we follow here, guys? If you remember, first initialize the weights, update the weight, initialize and think the function and neural network, and then train the neural network. Okay. So what we are going to do, basic steps we are going to learn as of how to use this activation functions and all. Okay. And how to configure our neural network. It's very easy. I ran this. Okay. So before I proceed, okay, I would like you guys to tell me what we are doing here. Okay. So let's go. Yeah, let's go slowly. We'll not go fast here. We'll try to understand each line so that in the deep learning networks and the recurrent neural networks and the transfer learning encoders, transformers, whenever we are learning, these lines of code would not bother you anymore, and we can just skip it or just mention that okay, these are the things that are being done and not worry much about it, right? So let's try to understand what is this. A class is being created. The class name is neural network. I will come like what we are doing in these steps. I will come. Let's try to understand what's happening here. Okay. So first a class is defined, and inside this class there are multiple functions that we are defining. What we are doing here, initiate self. Now self is something that we are going to call. Okay, so where is the self? One second. Hmm. Okay, let's proceed. I was just checking if the self is integral part of this neural network or it is being used separately. So here, this self is nothing but I'm asking the Python to initialize the neural network, okay, by itself. So after that, I will do a lot of different things, but I am first initializing the neural network. How I am doing so? Seed the random number generator to ensure reproducible results. What is the random seed? Let's say I'm doing np.random seed2. So it will randomly generate some number, okay. Now initialize the synaptic weights to a 3 cross 1 matrix with values in the range -1 to +1. What are we doing? In the range -1 to +1, we are assigning synaptic weights, like any random weights we are assigning. How we are doing? To the self that we initialized here, we are assigning synaptic weights. What are they? 2 into np.random.random, where it is a 3 cross 1 matrix. And there, I am talking about the range being -1 to 1. So since it is random, what it will do is generally it assigns any value between 0 to 1. Okay, it assigns any value between 0 to 1. So what's happened is once it's assigned any value between 0 to 1, if it is 0, then this whole value will be 0, right? And then the weight would be just -1. But if it is some other value, then we are multiplying it by 2, right? Let's say it will be any value between 0 to 1. So maximum it can be 1. So once it is 1, this total value would be what? This would multiply to become 2, and then we are subtracting it with 1 to get 1. So the range would finally become -1 to 1. Got it? How the range we are getting to getting between -1 to +1. Okay, so if it is 0, if the assigned value is 0, then we will get -1, and if assigned value is 1, we will get +1 here after the calculations, and obviously there can be any value in between, right? Now these are the things we are assigning a hyperbolic tangent activation function. Okay, so these things like tanh activation function is also there, like relu, step, and all, right? We have a tanh activation function as well. Then we have tanh derivative. We are assigning a tanh derivative for back propagation. Calculate the derivative of tanh function for back propagation. What happens is whatever is the activation function, we just need to do the derivative of it to like get used to the back propagation. Okay, so that's the mathematical concept. Whatever is the activation function, just do a derivative and it will like help you in the back propagation. Till now we are done. And then finally what we are doing some training activity. Whatever we assigned to the neural network, what we did, we mentioned that the neural network will generate number generator at random. It will have synaptic weights for a 3 cross 1 matrix. It will have an activation function, and it will also allow back propagation, right? And then once we are ready with our neural network, what we will do, we will start to train. Okay, so once we train, what are the things happening? Train the neural network through a process of adjusting weights. Here, in all the iterations that we are doing, we are just trying to get a simple output, then getting the error, then doing the adjustment, and then finally adjusting the weight. So this is nothing but training and back propagation together. Okay, let's not go into that deep, because whatever we are seeing here, right, it's just a base. Based on this, we have a lot of algorithms out there based on top of which we can do our modifications. So even if you don't like if you are not coding wise aware about this, no problem, you just need to know the concept, and still on top of that you will be getting these neural networks where these are preloaded. Okay, here we have taken an empty one, so we will be getting preloaded neural networks where all these things are predefined. These trainings will be predefined. All you just need to do is these neural networks will itself do the iteration, will calculate the output, then from the output they will calculate the error, then do the adjustments, and then according to the adjustment they will update the synaptic weights. And then one thing, I will come again to this. Okay, I will explain this line by line, don't worry, let me explain the whole thing. And once you train the neural network, we don't do test, we do think. Okay, we could also write test here, not an issue, but just from the understanding point of view, a neural network does not validate the data, but it thinks, because it's neural network. A human mind does not do, like, after it gets trained on something, it thinks, right? So similarly, neural networks also think and then respond. Okay, so once we pass some input, it will think and will then respond an output. The whole process is clear. Then I will specifically go and explain you how for each iteration the output is calculated, and then error error is found, then adjustment is done. I will explain. Can you please confirm the overall steps that we are doing is clear? Then only I will go to the integral steps of train. Guys, any questions till now? Yes, yes, I will explain. Definitely. Tan h, this you want to understand, no? I will explain. Give the curve for tan h. So as we had a curve for ReLU and all, this is the curve for tan h. Tan h activation function in neural network. It is basically a S-shaped curve, a hyperbolic tan h, a hyperbolic tangent that we call tan h. This is how it looks like. It's basically like a sigmoid, but just that the value is not between 0 to 1, but it is between -1 to +1. Understood, everyone? Same thing as a sigmoid. But why we are taking a tan h and not a sigmoid? The reason is this. One second. The reason is this. Because we are taking values between -1 to +1. So accordingly, we will have to take a similar activation functions, which can take care of all the records, right? Understood? Was that? Vikas, understood, right? Yeah. So till I need more yeses, guys, please. Okay, perfect. Now let's go ahead and understand what this each step is trying to say in this train function. Okay. Okay. So guys, the purpose, right? The purpose is the method train is responsible for training the neural network by repeatedly adjusting the synaptic weights. Now we will go ahead and see how it is done. First of all, we are seeing a for loop. What it does is the for iteration in range. What is the range? Range is number of training iterations. This line means we will iterate the training procedure for a specified number of times. That is number of training iterations. So whatever will be the value that we will give during week while we call this train function will be the number of training iterations. On each iteration, the network make predictions, calculates the errors, and adjusts the weights accordingly. So what it does on each iteration, the network make predictions. So here it is making predictions. Then it calculates the error, and then it does adjustments of the weights accordingly. After that, here if you see, there is also something called forward pass. Okay, this step output equals to self think training steps input. So whatever the input from the training steps, here what we are doing is we feed the entire training set into the network to get the current predictions. So current predictions is the output. Here self the think, what it does is the function typically does like two things. What are they? It calculates the weighted sum of the inputs through like this formula. The formula here is, let's say, hold on. The formula here is, let's say, y equals to x multiplied by weights plus bias. Okay. So this is the formula that is being applied when it is doing self think, right? And then it also applies the activation function. Okay. What is the activation function? In our code, the activation function is tan h. Okay. So this self think only applies the activation function. Don't think that activation function is going to get applied somewhere else. Here, what is being done? Obviously, the training set output in the training set, whatever the output was there, that is being subtracted from the actual output that we got, and hence we get the error, right? We get the error accordingly. And then according to that, we make some adjustments. So this adjustment, this step is also known as uh, gradient and weight update. Okay, gradient and weight update. What we do is we compute the derivative of the activation function. So see, first of all, we do self tan h derivative of the activation function like through the output, and then this particular thing, it returns what? It basically returns 1 minus tan h x of square. it returns what? This derivative. One minus tan h input x to the power square. Okay, this is what it returns. Now, this derivative tells us how sensitive the output is with respect to the changes in the input to each neuron. Now, what we do? After that, we multiply the error by this derivative. First of all, why we did the derivative? Because this derivative tells us how sensitive the output is with respect to the changes in the input at each neuron. Understood? So, at an input level, how sensitive the changes at the output end is, this derivative is able to tell us that. Okay, so how it helps us? It helps us by, like, it helps us to adjust the weights accordingly. Okay, so after doing the derivative, we are multiplying it with the error. So this step, basically, while multiplying the error, this step scales the error by how responsive the neuron is via the derivative. So suppose there is an error in a neuron, right? Now that error, we basically understand how responsive it is. Okay, and then what we do is we compute the weight adjustments. How it is done? We take the transpose of the training set inputs. So taking the transpose does what? It like, so that the matrix multiplication, when we multiply, right? When we do the dot product, so here it is a matrix multiplication. We are multiplying the training set input, the input values, with the error and the derivative term. So here what's happening? It yields the gradient of each weight. So that way we will understand what is the gradient of each weight and how much it needs to adjust accordingly. So essentially this calculates how much each input contributed to the error and thus how each weight should be updated. Got it? So we do the transpose and then we do the dot product. So here you see it is the dot. So here the inputs transpose multiplied by the error into this, you can term as sensitivity. How sensitive the error was due to that particular input, we get to know. And then accordingly, we get the adjusted weight for each of the inputs. And finally, we get the weights updated here, right? So this is how this train works. And then obviously we can do think. So think is nothing but predict, right? So guys, please tell me if this was clear or not. I tried to be very specific at each point. Guys, Vijay has said something. Tan h derivative function have two inputs, okay? Tan h derivative function, where is the tan h no, no, here we are passing the self value. It's not two input. We are passing the self and the input x, okay? Like input to the tan x derivative. Now, this is used for back propagation, right? This is used for back propagation. So what would be the input to this tan x derivative? Tan h derivative, the input would be the output function, which is used for back propagation. So that's why here the input is actually the output value itself. Now understood, Vijay? Yeah. Any other questions, guys? Any other questions on this, everyone? Guys, please comment. Guys, I hope there are no questions from this. Acha. Here we are generating random weights. However, in case of real world data, there are any algos that can be used to specify weights. Yes, yes, yes. We will see how it works. Okay, we'll see how it works when we have the actual data. I will show you those things. Mm, all these things. Train the neural network. Yeah, same thing. Like it's being repeated. Everything is same. Okay, we are just printing what these weights are, what these values are. Nothing else. Always start. These were always random by start. Everything is random in this case. Okay, yeah. But accordingly, like even if they were random, we also assigned the output values as well, right? So according to those weights, like the output that was being predicted was not matching. So that's why some error terms also occurred. And accordingly, that like we did this so that the error occurs and we will be able to do back propagation, right? We will give specific weights when we do it for I will tell you when we do it properly for next what to say, next specific use cases. Number one. Number two, this is something I guess we have already discussed, which is you can start with weights being random, no problem. Mark your weights being random. back propagation will take care of it. Okay, but yes, we do have some features, like we have some functions where it understands each input, and accordingly we can give predefined weights, right? For example, if some value is very important to us, some input value is very important to you, what will you do? You will give higher weight. Let's say column A is very important, but similarly column B is not that important. What will you do? You will give more value to column A, more weight to column A, and less value and less weight to column B accordingly, right? So that way we will have to do manually. But apart from that, anyways, you can do it randomly. But again, that is also random, right? No, 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 that is not random. If you are talking on a scale, for example, say out of 10, the importance level of column A is 6, whereas the importance level of column B is 2. So accordingly, the weight will be 0.6 for A and weight for B would be 0.2. So it's not random at all. Did you understand? Yeah. Okay. So here they are just printing, since they are random weights and everything is random. I'm not going there to show you what was exactly designed considering the new situation 100. What is this 100? If you can explain me. Acha, this one. Okay. Okay, I will do that. So here what we are doing is, let's then we have to start from this point. Okay, create an instance of neural network class. So here we are creating an instance, and then we are basically printing the synaptic weights. So what are the synaptic weights? These are the random synaptic weights. Here defining the training sets and input. What are the training sets, guys? Let's say the training sets input are three. What is the array? 1, 2, 3, 4, and then training set outputs. Outputs are 1, 2, 3, 4 transpose, right? So these are my 4 cross 1, 2, 3, 4. 1 array, 2 array, 3 array, 4 array. Yeah. So for all these training sets, input sets, there is an output 0. For this, we have this, and similarly for this and this. So there are 4 sets of array, and we have 4 output. Sorry, 4 sets of list in the array, and we have 4 outputs. We are transposing it. Okay. Now, what happens is, this is our define. We are defining the training sets and the output. Here, what we are doing is we are training the training set inputs and the outputs for an iteration 1000. Right. So here, what we are doing, whatever we did here, whatever we gave these values here, right? What we are doing, we are just assigning values here, nothing else. Okay, we are just assigning values here. Now, when we are training the network, what we are doing, first we are uh, printing the synaptic weights, and then once it is trained, we are giving it a new situation to think and then predict the output. So finally, it is considering the new situation. This is what it is predicting as 1. Like considering the new situation, the output it is giving is 1. Okay. What were the other outputs? The other outputs were like this: 0, 1, 1, 0. So this situation, on this situation, it was never trained, right? I gave it a new situation here. That's why it's written considering the new situation, for which it thought and gave me an output which is 0.0, 0.9999, like close to 1. Understood, Vijay? Yes, perfect. Okay, I will need a breather again. We took a 15 minutes break now. So for that, let's take a 10 minutes breather. Just we test. Ha. We think means test, that's it. So this is a basic how it works, right? We created a neuron, we added activation function, we added the back propagation using its derivative. We saw how it gets added, how it gets multiplied to the error term, and then how the inputs are transposed and multiplied to get the weights adjusted, right? Now when I actually show you back propagation in theory, you will understand it real quick. Got it? So for that we did, so that once you know back propagation over practical how it's done, now next section we are going to see how it works in theory. Got it? So it will be very easy for you. So I will like just give you a small like break, and then once we come with fresh minds, we will understand how back propagations actually work, how the weights are actually adjusted in theory. Okay, Saha? Yeah. Hmm. Okay. Let me get a 10 minutes, please. Okay, guys. Perfect. Now, training a perceptron models involve two phases. We already knew that. That is, one is forward propagation, and another one is backward propagation, right? We already discussed on that. Now we will understand, like theoretically, how it basically works, right? How a perceptron model works, how the forward press and backward press works. So we will go through an example. Loss and cost function I will explain you. Let's understand the backward propagation first. So here, what we are doing is we are considering a feed forward network where we are considering one example. Please pay special attention to these boxes that are present for the next 3-4 slides. So here, this box input layer here for the hidden layer, and then for the output layer. After that, how in these boxes the weights are calculated, errors are calculated, and then adjusted. So everything in like including the mathematical derivations are also present. Now you guys tell me, please tell me if you are like if you are interested to understand this derivation or you want to skip it. So whatever maximum folks say, I would like to do that. What do you want? You want me to include these derivations in while explaining, or you want me to skip it while explaining? I will do that way only. Guys, skip. Skip it, everyone. Okay. Can I get other responses as well, please? Guys, I need more responses, not just one. I'd request for more include. Vikas is saying include. Okay. If I have only at like even one response to include, I would like to do that. Okay. So we'll start from here. What we have done here is, guys, we have considered two input neurons, I1 and I2. Okay. We have assigned two random values, 0.5 and 0.05 and 0.1. Okay. These are the two input neurons. Now we have an input bias as well. So as we know, y equals to mx plus c, right? So we have a bias as well, which is considered as the intercept term or basically the bias. Okay. So for the input neuron I1, it is sending responses to two hidden layers, H1 and H2. Okay, two hidden neurons in the second layer. The responses going are, according to the responses, there are weights assigned as well. So I1 has weight 0.15 as W1, sending to H1, and 0.20, which is sending to H2. This is for I1. Similarly, for I2, we have the weights 0.25, which is called as W3, and 0.30, which is W4. We have a bias of 0.35, which is going towards both the hidden neurons of H1 and H2. Till now, it's clear, everyone? I need just one confirmation. Yes, clear. If anyone is not clear, let me know not clear. Let me know, guys. Clear. Now what happens is, as we proceed further, till this I have already explained. Now what happens is, when we go to the output neuron, here the hidden neuron is sending response to both output 1 and output 2 neuron, and the hidden response, like hidden neuron 2, is also sending response to output 1 and output 2, where the weights are 0.4, 0.45 for hidden neuron 1, sending output to O1 and O2, and H2, the weights assigned are W7 and W8, the weights are 0.5 and 0.55. Here, the bias is 0.60. Now, the expected output here for O1 and O2, expected output, which I'm saying, okay, this should be the expected output. It is what? It is 0.1 for O1 and 0.2 for, sorry, sorry, 0.01 for O1 and 0.99 for O2. This is my expected output. Okay. Someone is asking a question. Input layer weight addition is 1, but for hidden layer, not 1. No, 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 no. Nowhere input layer weight addition is 1. Where is it 1? Why bias increase during hidden? Is it all time? No, no, no. Just random. It's a process of explanation. Okay. For explaining, we have taken random values. You see, it's random 0.5, 1.5, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5, 0.55, 0.6, like this. Ha 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 ha. It's like that only. Oh, that way we are calculating. No, no, it's just coincidence. Huh? It's just like this. See, it starts from 1.5 and with a difference of 0.5, it goes till 0.60. Let's not get into what is the function of bias here. We are just understanding how it works, right? We are understanding the theoretical concept. Okay, Anup? Here, like nothing. Let's not get into that at all. Just understand how it works, how forward press and back propagation works. We are trying to understand that only. We are not coming to threshold right now. Okay? Because threshold concept we have already understood. Now, if we include everything in one go, we'll not be able to understand the concepts individually. Right? Got it, Anup? Can we proceed? Yeah. So this one is also clear. Now what will happen? We know how the input values and weights are calculated, and it passes to the like next neuron, right? Accordingly, what happens? We calculate the net of H1. So in this, like whatever value that reaches H1 will be called net of H1, which is calculated as I1 W1 I1 plus W3 W3 I2 plus like bias into 1. So here why B1 is 1? Okay, so whatever the bias. So this bias, whatever is there, right? This is my bias. Bias is what? 0.35. The bias is 0.35. So this is for the H1, and the net H2 is similarly I2 into W3 plus I2 into W4 plus 1 into B1, right? So we calculate what? We calculate the net for H1, and the net for H1 is coming as 0.3775. Okay. Now, what happens is here we are using logistic function like as the activation function. What we are using logistic function or the sigmoid function, so as to say. So to the output, net output, what is the actual output of H1? So the net output gets applied to the logistic function, that is 1 by 1 minus e to the power this minus of net of H1 is the actual output from H1. Okay. Sorry, is the actual output from H1. So what is this? This is 0.59 something. And here for H2, this like we calculate it in similar way, and this is my value. Okay, so here activation function is included. Now, similarly, when we as we calculated it for H1 and H2, the output values, we are using these output values to calculate what? To calculate the net of O1 that will reach the O1, right? And similarly, we calculate out of O1, output 1. So what is the output of O1? It calculates to 0.75, and similarly, output of O2 is 0.7679. Okay, this is my output value. Now, if you see, this is the calculated values. Fair enough till now, right? Now what happens is there is a huge error. Here we have like this is not actually the error term usually. Eta. Eta is nothing but the learning rate. How fast I want this change to happen. So it can be 0.01 would be like not good. So by layer we will adjust the weights. Okay. Now how these weights are actually adjusted, we will see. Okay. So this is for us to see. What we do is calculate the derivative of the total error. We were calculating derivative if you remember. So how we are calculating the derivative? We are calculating the derivative with respect to weight parameter 5. So with respect to error 1 or output 1, what are the weights parameter W5 and W6? So we will calculate the error with respect to each of the weights. Remember. So we'll calculate with respect to W5, W6, W7, W8. We will adjust it. Then we will come back to W1, W2, W3, W4, adjust it. Okay. Now what we are doing is DE total divided by DE total by DW5. This we can write like this. Can we write like this? Here, what are we doing? DE total by, we are writing D out 1 multiplied by D out 1 by D net 1 multiplied by D net 1 by D W5. Partial derivative, right? Partial derivative we are applying. See what happens if we do cancellations of numerator denominator. From this we actually get this. Now why we are doing so is because it's easier for us to calculate these values individually, this value individually, this value individually, and this value individually. It's easier for us to calculate. Okay. Now as they are exactly. They are independent. No, so these are like a lot more easier to calculate. So what is this? This is delta for 0, 1, so-called, we can call it like DE total by DWS. So what are we calculating it for? We are calculating it for output 1, right? We are calculating it for output 1. So by default, we can write delta 1, right? Partial derivative of for output 1. And these values, what are we doing? We are calculating here. We already know these values. I will show you. We already know this. So here we are calculating the complete error. We are getting the out, we are getting the net. We have already calculated these things, right? And once we do the calculations, we get the DE total by DE out as 0.4771 like this. Okay. And once we get this, what happens? Like we calculate all the values. See, we are calculating everything. All these values we are calculating. We are calculating out by net like this. Then we are calculating using the activation function, everything. We are differentiating the activation function here, if you remember, right? We do differentiate the activation function in order to calculate the weight. We are doing it. And finally, we calculate D out by D net. After doing everything, we again calculate net. So we are basically, what are we doing is we are calculating these values individually. These values individually we are calculating and we are putting it together. After putting it together, what is this we are getting? We are getting this. Okay, 0.0815 is what we are getting. Now, this is what represent how much does the total net input of O1 change with respect to weight number 5. So with respect to weight number 5, this is by how much the input of O1 changes. So accordingly, what I will do? I will just go, yeah, partial derivative only. I will go and will apply this formula to the existing weight. We subtract this value. Why? Because this, by this much amount, it's changing the input value, right? So if we change the input value by this much amount, we should expect that there would be no error. We should expect, right? And here, eta is nothing but the learning rate. How fast I want this change to happen. So it can be 0.01, 0.1. So it ranges between 0.01 to 0.1. Okay. So you see the weight W5 is updated. Earlier, this W5 was what? Earlier, this W5 was 0.4. Now it's 0.35. Similarly, other weights, like W6, W7, and W8 are updated as well. And then as these are updated, we proceed to update the weights in the first layer as well, right? See, the weights in the first layer are also updated. And finally, so here it's being shown for only one, that is W5. And then finally, once this happens, again, we repeat the same steps to update the weights in the first layer, right? For W1, W2, W3, and W4. And once the weights are updated, again, we go with forward press, right? Now, since the weights are updated, what will happen? I will expect a lesser error or zero error. And I will keep this iteration going till I am receiving like zero cost function, like zero error, or till the time the number of iterations I have reached. Okay. So suppose 1,000 iterations. In 1,000 iterations, if I have not reached
in today's session, and I have shared the server link in the chat window. If you like today's